Okay, so I guess we can start for today's session. So we are almost halfway for this course of techniques on material characterization. So it is week 6, and week 6 assignment is due to this time, and we are like more 6 weeks to go on. I don't see many people have joined, but it's fine. You can always go back and look at the recorded lecture. So last time it was all about TEM. Well, about me. So I'm Jagrati. I'm a PhD scholar at IIT Gandhinagar. I work in the medical ultrasound engineering lab, and I'm a PMRF fellow. So I'm taking this TA with Professor Shivayan Roy from IIT Kharagpur. Okay, so that's about me. And so last time we saw about TEM, different characteristics of TEM and properties of it. We looked at the assignment though, and we didn't go into that much detail as it was given in the lecture slides because I didn't feel it was that much needed. And you can always go back to the recorded lectures. You can always go back to the lectures that are there on the NPTEL platform, and you can all go have a look on them. If you feel that okay, you need some information, you can also let us know beforehand. So as just I guess 2 days before there was a live session from Professor Shibayan Roy, and I guess some of you might have joined for that particular session. So you can be again once a session would be held again, and then within that particular session you can post your doubts in ahead of time in advance, or else you can also ask your questions in the session whenever it's being conducted. Similarly, for sessions like us, also, you know about me, and you know that we meet regularly on every Saturdays, 5 to 7. So you can have your doubts already done, or you can also post your doubts on the discussion forum, as in how it's comfortable for all of you. Okay. So last time we just missed out on this particular part, and I felt it was pretty relevant for cases where you look at the applications of electron diffraction. So diffraction. So one of the ones that have been considered. So we all know that okay, when you consider crystalline structures, it's always about the plane when in which particular plane the structure is, the atom is lying in which particular axis. So from there you can get to know, or you can do that structure identity confirmations, and these have been done based on the phase and the orientation of your specific material. Okay, so okay. So, is it's lagging, but it's fine. Yeah. And then there's also one another thing called as dislocation. So that's something different for TEM, which does not usually occur in SIM. So we'll just see how and what it occurs. So what you see over here are nothing but the spotty diffraction patterns. Okay, and this type of diffraction patterns, if you see and go, this will like after a point will converge into rings. So if I just have to show you that particular pattern, I'll show you SCP diffraction. No, just acidic diffraction. Yes. So if you see over here, this is something like for a crystal-like material, and it's like spotty for now, and it just how it's like a specific technique which happens in TEM. And after some points, these patterns will appear as rings. So if you just see here, so after some point they go and resemble rings. So in a way, we have a relationship in between the spot and ring diffraction. Also depends on the metal that you're trying to image, or the material, your specimen, which particular constituents it has. Okay. So from here, if you just see, it's like, why do we need this particular spacing of this indexing of the diffraction pattern? Which particular face-centered cube is it? Are we following for it? Will definitely tell us information about. First is like help us measure the camera constant. Next is like the diffraction contrast mode, the unknown material. So how do we know that? Okay, if I don't have that much specific information about my material, and it's just the first time I'm trying to image it, I want to see what else is inside it. So from the lattice parameters and the symmetry, although it's quite difficult or complex to get to know from these two parameters to this one, but yes, people do so, and they have been successfully able to do that. So of course it's possible to do. And then they can do like measure the interplanar spacing of the materials, the exact orientation of it, which particular plane or axis it's following into. Now you have this particular vector here, the cross product of two vectors here, and that is nothing but will tell you about the dislocation contrast, and this is something called as dislocation Burger vector, or Burger vector, how you call it. So one of them, this particular B is nothing but for the Burger vector. It specifically relates to you about the dislocation contrast, and the first one is nothing but the diffraction vector on the zone axis. Okay, so if I just have to, so this is your diffraction vector on the zone axis, and this is your Borger vector. And in a way, it will tell you information about its magnitude and its direction. Okay, so both the informations you will get from here. So this is nothing but the one contributing to the dislocation contrast. If it is zero, then we say that, okay, dislocation is there. So the dislocation is the one that is being diffracting. If it's non-zero, then we say that, okay, it's not there, not present over there. Okay. So you already know till now that, okay, what the dark field imaging is. When do we see dark field imaging? When the direct beam is not allowed to pass through the aperture and only we are adjusting the aperture in a way that our diffracted beam is passing through, right? So you get these kind of patterns in there. So here are examples. So for the bright field, is like we just allow the direct beam to pass through, whereas however for the dark field, what we do is like we'll have the direct diffracted beam to pass through the aperture. We'll adjust the shape of the aperture in a way and the direct beam would be blocked off in there. So these are the modes in which TEM imaging can be done. Now for dark field, it can either be on axis, can either be off axis. Based on the on axis, off axis, your diffractive beam and the aperture angle will also differ, and you will see different diffractions pattern out there. Okay, so I guess here you are looking at different structures. So yeah, based on this diffraction pattern that you look on your image. So this is nothing but not mostly the ring type, but it's something like spotty. So if you look at different areas and zones, you'll be able to get different characteristics and contrast. So this characteristics and contrast are only due to that particular certain area in which your diffraction beam is there, where a diffracted beam is allowed to be passed through. And these are like certain combinations which are made with the objective aperture so that it can be formed as a bright field in the C and E1. Okay. So after we see that, we know that what was the difference in between bright field and dark field and how contrast can be generated, how diffraction helps in that case. But we can also get to know about the first. So we always have two things when we are concerned with a signal. So you have some. Hi,
Devi,
yes.
it's my kind request. Your speed is very difficult to catch that one. That
Okay.
speed, you are going like a reading speed. It's called a reading speed. The observation that as a audience, we need to observe the word before you are talking to the next word. So that seconds, it's not possible by fraction of second, ma'am. Any human being, whoever is clever or smart. So, I'm keenly try to gather or adopt or observe your words to make a what is that to think about that. Just listening is different. After listening, it needs to enter into our memory space, and it needs to be processed, and then it will carry to our memory. Then it can be expressed when it is needed. So such kind of process is demanded for the effectiveness of these classes. Your speed needs to be reduced three times slower than what you are going the speed, what you are what is ejecting the words from your mouth. That needs to be three times slower, ma'am. Then only it will be become a meaningful section, I believe. It's my kind request, kind opinion.
Sure, sure. I'll try to. But the thing is, for these sessions, we aren't expected to teach you. We are doing that because we feel that people are not looking at the slides. And then we just have to summarize and go through the slides. So we expect that you have read through them. And of course, I'll work on my speed or speech. So I'll try to reduce my speech however it's possible. All you can always go to recorded lectures and can slow down the speed over there. I have this issue of speaking too fast. I can try and lower down my speech accordingly. So, when we were on phase identification from this area related diffraction, so where what we see here is if you have a signal, you'll have a time domain component to it or a frequency domain component to it, plus you'll have a phase component to it. So now this phase and the magnitude of your signal will contribute to the diffraction pattern, and in a way you can get information about the structural identity. So how different atoms are placed from each other, what's the spacing in between them, how the diffraction pattern finally is coming along. So here the thing is that this point, at this particular point, we exactly won't be able to carry out because we don't know what's the exact maths inside it, how it's being followed through. We only know about the lattice parameters, we know the zone axis, we know zone planes. We'll be only able to identify the exact indices, how they are being placed. But from those indices, how these distances come along, you have this relationship. Of course, we derived this relationship last time, but just to get in, because these all are like approximations if you just assume some spherical scattering. But if not, and if your structure is different, your lattice is different, this would be different. So identifying information from phase and from its orientation, how the structure is being placed, if the material is unknown, gets quite difficult and complex after some point. Okay. So here, professor only showed that, okay, this was some unknown material and they were trying to characterize its structure. They were trying to say that, okay, how much it would vary. So they dot this different orientation line, and across it, they were just trying to propagate that how beam is passing, which particular plane it would be passed. So how the interatomic distance is varying. Based on the interatomic distance, they would like be confined that, okay, probably this material with that. So you'll have a lookup table every time. So within that lookup table, that is why how chemist comes up with the way that, okay, this composite can be formed, or this particular combination would work with, or let's just work with this material. It would be compatible for our application of purpose. So you can do these things, but I have never really went to the core deep maths of it, and not as nice like professor has shown it to us. So these are like the things that can be done in TEM, and that's why TEM is quite complex if you see in terms of interpretation, because here your sample is almost electron transparent. So you are having information or about almost all layers of your sample at across all depths. So interpretation there becomes quite difficult towards the end if you don't know much prior information about your specimen. Then it's the same thing for orientation. So for orientation, the basic idea was that if you have your sample in one particular plane, you take its orthogonal component along the second plane and you get information about that plane. So it's similar to how you take tangents. So if you have tangential direction, if you have a surface like this, you take a tangential direction, and then that tangential direction will define your zonal axis plane. Based on that zonal axis plane, you'll be able to tell about its direction and magnitude. And from there, you tell us about the interatomic spacing. Essentially, the first thing that is being done over here. But exactly how it's being done, I'm not at all aware of it. Or I guess this thing was also. So it's just the application that you should know that, okay, we can also do these things. But when you actually want to do these things, you should be like a core material people person or a core technical person to understand that how it's being happening here. Okay. So after that, here are also like you can change these properties and lattices in between different materials. It can be HCP, it can be a BCC, and between different structures, the lattices can be changed, and you can derive relationships in between them. So here the relationship goes like initially we had HKL, now it would be increased from there, and it's all component is like, and a relationship comes from those angle to angle in between these two, like alpha versus beta. Of course, we know that there's a relationship in between HCP and BCC based on how the structure cubic centers are being placed. So based on exactly the structure, here we know that it's body center, here it's hexagonal. So you can get information about the structure from there, but the inter-element spacing, the interatomic spacing, all those things will be the one that will define that how your lattice is being placed and what particular element you are trying to find out there. Okay, so it's like here's how you see that. Okay, eventually from spot, you're finally able to see some rings into the structure, some periodicity is starting to come. So then it's like you take different components along the matrices, you see that how it's being changed, the direction will be changed. Here you see something as HCP, here you see something as BCC. So that's how the structure are being varying, but exact relationship is still unknown, or people who try to find out, they just work on finding it out. Then there's this thing that is dislocation contrast. So as just said previously, this is nothing but very invisible, or is like has a weak contrast. That's why what we do is like we take this cross product, and the first one is for diffraction related. This is for the dislocation related. This is like our Bourdieu vector. Uh, this one. And then as and when our diffraction is present, dislocation contrast is there, it would turn out to be zero. So certain planes near that particular dislocation, when they are bent, bending will increase, and hence increasing the distance. Wait, what happened? From the dislocation. So here. So if these planes are bent, so they are strongly diffracting. So you know when something diffracts, when light diffracts, exact same thing. When it is bending, so the intensity will be reduced at that point and diffraction would be increased. So your direct beam would be reduced and your diffracted beam will be increased. So similar effect that it will appear as dark in a bright field image, whereas it will appear as bright in a dark field image. Okay. I hope you're able to follow now. It's like no sarcasms here, but I really hope that you're able to follow up now. Okay.
Yeah, yeah,
So
follow.
similar, yeah, okay, thanks. So here we just say that, okay, at how particular angles our matrices is also varying. So you change the orientation, the dislocation. So amount of diffraction eventually will play a role into the contrast that you are seeing in your image. Okay. So how it's being done is just two simple phenomena. One that's based on your direct beam, second that's based on your diffracted beam. Everything depends on your objective aperture. So nowadays you have this programmable apertures. So you can just input into a system and then tell them that, okay, I want this direct beam to come and interact with my specimen. Accordingly, I'll have my bright field image to be generated. Or in systems like there are systems from JOL, that JEOL from Japan. These systems don't need that information. They would be like, okay, just bright field, dark field. Will ask us for on axis, off axis. The aperture will automatically be adjusted based on the sample. Because in TEM, we all know that our sample size, our specimen size is inherently related to some microns. So it's not even like a SEM where you can have like at least maximum 5 of sample. So it's very smaller sample and very thinner sample. So yeah, they have done like the substructure studies. You can see the faults from the structure. So everything relates to the it's like, what do you say? Yeah, diffraction. And not only diffraction in this case, but in this particular this beam profile that you're looking at. So this spherical profiles, based on the spherical profiles for that each area, this each lattices will give you different diffractions through it, and that will help you account for the structural information from where it's coming. But of course, for its maths, you'll have to study it into deep into it. Okay. And that being said, we'll now go to SEM, which is like a topic for main topic of interest for this particular week. We have previously looked on for SEM. We went deep into SEM for some time, but it was all like we were trying to generalize it for electron microscope. So now you all know that what SEM is. SEM stands for scanning electron microscope, and this is transmission electron microscope. Since both are electron microscopes, we know that their source. The electrons so the source of is like source from which you're getting your input is exactly the same, that being said, as our electron gun. But however, the other things might vary. In that case, it can be the way it's being detected, the way it's being captured might also differ. So the detection signal would differ, or the way of detection we are trying to detect it would also differ. There's also one other difference in between TEM and SEM is that, so we have very high voltage electron gun passes through it. So that can vary almost as like 100 to 300. What happened? 100 to 300 kilo electron volts, whereas or kilo electron volts, whereas in SEM it's like mostly 10 to 30 kilo electron volts, or even sometimes lesser than 10 kilo electron volts. Okay, so based on that, we know that for SEM, our specimen need not to be very transparent, electron transparent. So our specimen can be opaque, and that can be thicker with relatively with respect to TEM. Okay, and here our specimen is nearly electron transparent. Should be, because that is how we can know about the structure. The images that we get in SEM are like more easy to interpret. Why? Because they tell us only about the surface information, the topology, sorry, or structural morphology. Okay, so you can only tell about those things. So it's just that, okay, what you're looking through your naked eye, it's just magnified to a point. So can someone tell me that how can you relate optical microscope to TEM and SEM then? It's like just some revision from our previous basics. So which particular mode of optical microscope is more similar to that of scanning electron microscope, and which mode is similar to that of transmission electron microscope? Okay. So when you have your optical microscope, of course, the structure of microscope is nearly the same. So, but when it's being operated in reflected mode and when it's operated in transmitted mode. So here, when I talk about reflected and transmitted mode, you might know that what's the difference in between both of them. Transmitted. Reflected and transmitted mode. So the reflected mode is similar to STEM because we no longer have the objective aperture and objective lens down is like after your specimen so that it focuses and gets your energy back to your camera and source. It will help you magnify. That is just in transmission electron microscope where or only in transmitted optical microscope where after some time you have some adjustments to be made so that your image gets better and you can focus and can look at different points. Whereas in SIM, it's just the reflection of the electrons from the surface. So it is similar to the reflected electron microscope, SEM, and whereas the transmitted one is similar to the TEM. Okay. So can we say that it's like so that being said, okay, we know about this that what we do is like we have it's a type of electron microscope that will produce image from the samples by scanning the surface with a focused beam. Now we'll just at each and every point we'll try and go to TEM also so that we know the exact differences in between SEM and TEM so that it all revisits our mind again. Okay, so this is like with focused beam of electrons, whereas what was TEM? So here we are scanning the entire surface with a focus beam of electrons. So we are just like sweeping the surface. We are raster scanning the surface. Whereas in case of TEM, it's just a primary beam that is interacting with your specimen. It can either interact within direct beam or it can either interact using diffracted beam. Okay, so it's just spot by spot. It's just one spot. It will look into, tell you all information. Then you move to the second spot, get in all information and all. It's not like SEM where it will like keep on accumulating or keep on concatenating all the image features and then finally give you one image. In this case, you have an arrangement that, okay, you have one set of lens here, you have your specimen here, you have another set of lens here, and then you have a camera source here. So here it might focus, here it might focus something like that in TEM. Whereas in case of SEM, it's just your specimen, you have your gun source, it will go and it will reflect back. So that's how it works in SEM. However, this is how it works in TEM. Okay, so I guess that's it. So what we are doing is we are making a raster scan pattern and the position of the electron beam will nothing but is combined with the intensity of the signal, hence to make an image signal. So what is being scattered back, the detected signal will be produced from there. The resolution that we can get here is like till 1 nanometer. But if you remember from 10, we can go till angstrom level. So it's like we can go till how we can detect an atom. So that's how the difference in between SEM and TEM is. But we always know that, okay, SEM is much more easier to work with and TEM is more specialized, whereas TEM is also more expensive with respect to the SEM. It has more specialized detectors. In terms of specialized, what I say, because our chamber in TEM is very limited. The size of the chambers are also very limited. Whereas in SEM, we have much enough working space. We almost have like 10 to 15 working space apart from our specimen where we can do some other kind of analysis that even if we want to, we can insert multiple detectors at the same time. Whereas in TEM, we do not have that much space. It's just only doing one particular operation at a time. That operation being said is nothing but beam that's passing through your condenser lens, going to your objective lens, finally making an image for you. Okay. So that was a difference. That being said, here also they have given one such example for it. So for electron microscope, it just goes here. Whereas for transmission microscope, you see you have a condenser lens, it will go to your sample or follow on your sample, then your objective lens, you again converge, and then you have a screen where your image is being made. Okay, so specimens are in SEM are nothing but are being kept at very high vacuum. When I say about high vacuum, it's like 10 raised to negative 7 pascals or negative 5 pascals, 5 positive 5 pascals, like that. So, or in very lower vacuum also. So, these conditions might also vary. You can like vary. So, it's very diverse. So, field of SEM is very diverse. You can place it for n number of applications, whereas for TEM, it's very limited. And only people who are like material scientists, they can only work on. So, previously, from our history, we all started to work with TEM. And when we worked with them, it was like two people who were like honest and Noel. These two people who were trying to make a system, but at that time when we had this high voltage electron beam which was passing in for the stem, it was we were not able to raster scan this particular beam for SEM, because hence after that some time this one entrance he came up with an idea that okay, we can perhaps reduce the voltage of the electron beam and make it focused, can demagnify it because we don't need that much magnification, and can perhaps raster scan is like scan the entire sample, and that way I get the entire field of view where my sample is being placed in a particular one time only. So that will give me much more inherent contrast, and that won't be that expensive and that much time taking with respect to SIM. So y'all, but it's like if someone has previously worked with TEM might know that okay, what's a sample preparation for TEM is like. It's very, very difficult. You first need to have a very specialized grid where your sample is to be placed. You take that grid with respect to the size of your specimen, then you place it. Now the container also won't have that much space. So for that, you need to prepare your sample in a way that it's almost dry, vacuum can be created. Whereas for SEM, all these things are not needed. Of course, for TEM, these things won't be needed. If you have a cryo TEM, then things your life would be very easy. But mostly institutes don't have it, and it's very rare to have it. So that's why in my institute at IIT Gandhinagar, we also have two SEM. We have one is like the regular one, second is analytical one for elemental analysis. We also have a TEM. I haven't used it that much, but yeah, we have Jules TEM here. So this is the same system from IIT Kharagpur's lab. This is like Zeiss system or Zeiss, how you pronounce it. And it's like we usually so we previously saw that we what different types of electrons that we get. First is the secondary electron, next is the backscattered electron. How you see surface differences, how you see structural differences, the energy of the electron. So our higher atomic number elements and the lower atomic number elements will govern that which particular electrons are passing through it. Also, the voltage through which you're passing your electrons into it will also depend on it. So, based on accordingly, you can always for one particular element you can make a secondary electron image. You can also make a backscattered electron image. So, in your scanners, you might have it written as, or in your SEM images as BSI, and you might have written it as EISIE. So, this kind of images are also written. Also, we have images which say LM, which say HM, that's being said called as low magnification, high magnification. Then you have something called as WD, that is your working distance, which tells you that if you have your specimen, you have your electron gun here. So that is nothing but the working distance is the space in between your electron gun and your specimen that will eventually tell you the size of the sphere, the scattering sphere that's being made. So something that we usually used to call as a sphere, pear kind of shape. So that scattering sphere will also depend on the working distance. Okay. So I hope the terms are okay here. So here, usually it's tungsten, so normal electron source, or it can be thermionic emission. But nowadays, people have stopped using this because those are like very expensive, very high maintenance systems, and they have started working with field emission guns. Of course, they also need very higher vacuum to be placed, but with respect to the maintenance of these ones, people may feel it easy to work with the field emission guns. Temperature also need not to be that much higher, which is when needed, because when you're doing thermionic emission, because energy heat would be created that much. And yeah, they are being used also for one of the application which is like most useful to increase the resolution of your imaging. Okay, so the maximum voltage that we go over here is like 30 kilo electron volt, whereas for TEM it's more higher, we just saw. So judging from it, do you think that we can use TEM, a regular TEM, for biologically active samples or something as carbonation samples where you have carbon in it? Can we use TEM for your biological active samples? or can we use STEM for it? Which one? And if we can use STEM for it, why? And if we cannot, why?
Can you repeat me the question, ma'am?
Yeah, so given we have our electron guns voltage is so high for TEM, whereas for it's lesser for SEM, it's like almost order of 100. Can we use TEM or SEM? It's like which particular modality can we prefer for or comes first to our mind when we want to image a biologically active sample?
Biologically active sample is TEM. The reason the TEM it is biologically it is feasible, compatible because it's not getting cheated or it is not spoiling through the TEM. And it is also the one factor it should be transmitted. The biological samples are mostly transmitted. But in the SEM, it comes, as I understand that, it is the metal, ceramic, polymeric, like a high dense sample, which can, I can say, fragile kind of sample. So that the reason the electronic, the primary, both using the same sources, but in SEM sources is 1 to 30 kilo electron volt, which is very high. That's the reason, main reason, comparing to the source and that strength of the primary electron gap. This is makes sense to justify our decision why we are not able to use the biological sample in SEM.
In SEM. Okay, I guess the second point was okay. I felt it was a bit more logical. But for the first point, if we just look for TEM, the voltage is that high, your sample would be burnt easily. Or your biological sample won't be biologically active anymore. And so, which we prefer TEM, but we prefer to do it using the diffracted beam, the secondary beam, and not the bright field, the direct beam. So it's always dark field imaging that we do for biologically active sample in TEM, because now in that way, the most of the energy that's being passed to the electrons is now transmitted and you get some energy that's being deflected by the lenses. Whereas in kind of SEM, you can always go and prefer SEM for biologically active sample, and that is the first choice people do, whereas TEM is much more specialized in that case, and SEM can be done because mostly your biological samples aren't that electron transparent. You need to do something or coat it with something so that your samples becomes active. Whereas in kind of the same, it is much more preferable because it allows your electron opaque sample also to be imaged. And what you need is like when you want to image, you sometimes only need the surface characteristics, the surface morphology through it. You don't want to know that what's inside it, because for biological people, they'll always know that, okay, what's inside it. They just want to see that how it's being affected. Probably some drug they're trying to go give to their cells or something, and they just want to see that if it's loaded into the nucleus or if it's loaded outside it, if it has intake in it or something like that. So first thing was that, okay, yeah, if you use this much higher voltage using a bright field one, that's a direct beam, your sample would definitely be burned. So people don't do TEM in that case. Also, if you have a cryo-TEM, you can always go and prefer cryo-TEM for it, but not for the regular TEM. It's just only preferred for the diffracted one. Okay.
So the answer will be for the biological sample. We can use SEM because of the low electron volt compared to TEM, right, ma'am?
Exactly. Yes. Yes. Exactly.
But SEM, if we are using it, there should be a coating, and there is not a direct beam, diffraction beam will be used for the biological sample.
Exactly. Because you don't want your sample to be, because once you do TEM, you won't be able to get your sample back. It just lost. Whereas in kind of SEM, you can recover your sample back. Of course, you don't need it back because you have made that sample specifically for imaging. But you would want to do further characteristic analysis on that sample. You need your sample to be recovered. So probably for TEM, you won't be able to use it when it's direct field or direct beam. That's your bright field imaging. Of course, for dark field imaging, it's much more safer for your sample, but people do prefer only SEM for that because the resolution is mostly apparently enough if you want to do a SEM imaging. Because If that's not enough, you want something more, you want your resolution to be much more higher, you go and do some confocal type of imaging, or you do something as that of ALS or those kinds of imaging, where you are just looking at the structural characteristics and you are or only about the surface of it or the nature of your surface. So that will inherently just be dependent on your specimen. So in that case, you won't even harm your specimen. So of course, in both these ways, in when we are directly talking about electron microscope, the electrons are the ones that are being interacted with our specimen, taking some electrons, knocking it off from certain directions, and that's why we are getting that characteristic signal. Whereas in case of light microscopes, we won't have those systems. Photons would just be refracted back, reflected or transmitted back. So that's much more safer in terms of your sample, for your sample care.
So here, ma'am, that all the biological sample is contains atomic electronic configuration, you mean, which is mainly semi secondary electron and backscattered electron.
Backscattered electron.
Secondary electrons coming from the surface of the specimen. The backscattered electron is penetrating, going to the nucleus, and it is scattered. Then it is coming as the same, almost the same electron volt of the primary electron.
Yes.
So I'm having little bit of what is that suspect that all biological sample having nucleus electronic configuration, that is feasible now, because the metal, yes, all having atoms electronic configuration is there. The biological sample like tissues, blood, or virus or bacteria, these are all the things how we can say it's a living organism, might be, but how it is having nucleus, electron, proton, and all.
So, well, it's not electron transparent. No, those are like opaque.
Opaque, okay. What means that is the light cannot be transferred.
Exactly.
So,
It cannot be transmitted through it. It will only diffract back or reflect back from the surface or till some depth. That's why people do confocal kind of imaging or like a SEM for it. They rarely go for TEM if they want to do that structural
yeah,
analysis.
secondary scanning electron microscopy works with the specimen atoms. Okay, the specimen is the primary electron atoms is interacting with the specimen atom. That's a secondary
Yes.
electron.
Secondary electron.
Then the primary electron beam is interaction with the nucleus. Then it is becoming a backscattered electron.
Backscattered electron.
Third one is called inter-electron excitation. That it is become a two-category X-ray characteristics.
Yes.
One is
After.
angle.
Yes.
Other
Yes.
also it become a K shell to L shell. Then there is outermost one is jumping. That is becoming
Yes.
angular electron.
Angle. Yes. Auger
We are all
electrons.
talking about that atoms, electrons, protons, neutrons. Such things are available in the biological sample now. Without that, some images is not possible, ma'am. If there is opaque, right? Opaque, I understand. The it's opaque is the meaning of which is transferable to the light or electron, which is not transferable. Okay, opaque is not to qualifying the sampling criteria of the SEM, ma'am. The SEM sampling criteria and the TEM sampling criteria is entirely different. TEM should be transparent or maybe diffraction. But there is a thickness is entirely different. You cannot go for the more thickness. There is some specific thickness is there. So there is no any electrons, neutrons, protons, interactions, and then that the images magnification. It's not found. It is entirely through similar to the optical microscopy of magnifying lens. So whatever we put, either it's a bright field mode or the dark field mode, thickness, and mainly thickness. It's like a small, the school boys are playing with the magnifying lens. Such is become a more scientific, sophisticated instrument is called the TEM. There is no any chemistry, much more is not involved in the TEM. But when it comes to the TEM, there is a chemistry background. People can understand that working structure. Non-chemistry people, the K, L, M electronic configuration, then it's become a whole one, K to L, that is a jump. Then there is energy is released. Then this is called the X-ray characteristics. This is totally looks like those that element has that atoms which have the electronic configuration, which is capable to qualifying the cell sampling requirement. But here, biological like tissues or virus or bacteria, where we can have this kind of details. This only I have curiosity. If you provide the details, it will be more appreciated.
So you want to ask that if biological samples have those elements, atoms like that?
Yeah, yeah.
What do you think? We don't have?
I don't know. I don't have idea because, for example, coronavirus which is came, we can able to see in 10 months.
Mm-hmm. So, well, do you think that you don't have any elements in your body?
Element is there, element, metals, everything is there in the water and everything. But really, I'm not a biological student. I'm a chemistry student. So biologically, sample having this kind of electron, proton, atoms, living body has some atoms. But you are taking that very small living organism. So such things having atoms is there or not really? I'm not familiar. I'm not studied into that. I have not come across that kind of what is that speech or article. I have not seen that one. The biological sample also what is that give the electron interactions or K shell, L shells. We studied this is in periodic table elements. We
Yes.
never think about that the periodic table element kind of electronic configuration is also applicable to that what is that living organism. That I'm not. You can explain. If or I can refer it with DeepSea or ChatGPT. I will shoot the question. I can get more time.
No. So what we can do, we'll have this thing. I can prepare one detailed slide on it. I'll tell you in more detail for it. I guess that lacks some basic. So we'll have to see and so not see, but we'll have to show you, okay, why can we image metals, why can we image elements, and why it's actually relevant to biologically active materials, and hence how can we do same for it? How can you see electron interaction from it? So that's like a very in-depth, or I won't say in-depth, but something that's fundamental to be cleared out. So perhaps in next session, I can have very detailed side on it. And first thing that we'll do on the beginning of the session, we'll just clear that out and we'll show this. Because for that, you'll need some schematics. Without schematics, you won't be able to understand that part. It's like something that we teach like very in beginning of this electron techniques, or we know that, okay, so I'm not a biologist, but yeah, I'm a biomedical student, but I have been taught these things. So yeah, I can, but that's something that I would like to say that if I just show you in this particular span of time, it would be very difficult for you to understand or follow. I'll have a slide for it also so that I can give the material away to you guys on the platform and I can directly give it to you.
I have asked the same question in that the previous live section about
Which one?
previous live section which running by one of your well-known person, I believe. What is his name? I asked the same question since I am working in the gas industry. So we start about the discussion gas. For example, the electrons are jumping here and there. Okay. If my sample is, for example, neon, xenon, krypton, it's most ionization energy. There, what is that? Jumping the electrons or removing the electron is completely impossible. So if the principle is needed, removing the electrons of the K shells, it is impossible in xenon and argon. Maybe it's possible, it's a very high electron energy. So this is the distance. And then the person is that there is no way this electron beam can work in the gas sample. The reason, that's what we are making vacuum. Why there is even that atmospheric oxygen and the nitrogen, it will have that very big consequences. I don't know what is the consequence. That's what we are making vacuum. Then I asked the question, which sample? It is metallic and ceramic and hard polymeric material. I said, biomedical, it's possible. He said, no, completely it's not possible because it's element, crystals, what is that? Metals, alloys, ceramic, and the polymer. This is what he explained. So then I convinced myself why the biological is not possible. Because of this electronic answer. But the same thing I come to you, but you having different, what is the thought? You said that there is cells also having atoms, but can also occasionally also is there in virus and bacteria. I'm eager to know that. I'm eager to learn.
Okay, so I'll just give you a basic hint here so that you can go and read. Probably next class we'll more talk on it. So what do we have in our body? We have different cells, we have tissues, something that eventually make up an organ, we have blood flowing through them. Okay, everything will have a biomolecule in it. And that biomolecule will essentially, how do you say, will have some proteins, lipids, nucleic acids, carbohydrates, all of those things, which are made from these natural elements, which are like carbon, hydrogen, oxygen, nitrogen, calcium, iron. We all have this in our bodies. With respect to how we have these vitamins which are being placed and how these vitamins vary in our body. Based on it, if you see one particular organ which is like very efficient, has very uh, more or maximum, how do you say, it's like maximum of that particular element, you have some diseases across it. You develop cholesterol due to deficiency of something, due to more increase in some levels. So these are always due to the inherent natural proteins, nucleic acids, lipids that are there in your body, which are essentially these natural elements due to these elements. Based on that, you have this natural biomolecules that are nothing but something which are due to shared carbon bonds. And based on the shared carbon bonds, of course, we all know that something as hydrogen bonding that's being placed over there. So you don't think these interactions would be there then?
Yeah, I'm understanding. There is something.
Exactly. So then after that, also so to give you some example. So if we have some digestive related problems, okay, we all go and take some soda. When we do that, there's some redox reactions happening into our body, something which has been oxidated, we try and reduce it. That's always due to some element and inter-element interactions. So we all have that, but we don't really take it to an atomic level like KLMN. We know that, okay, there are elements, there are certain elements. We always relate to that atomic number with respect to mass of it. So when talking about SEM, people always relate the contrast to contrast, mass thickness contrast, density contrast. They no longer look at the atomic contrast, or they don't say the structural contrast, they because they are only related, or they are only limited to the this surface level morphology or topology of the surface. So they no longer want to go into the atom, they are just related, or they are just confined to the surface of it. So that's why the inter-element interaction, the interatomic interaction is always the point to be discussed in TEM but not in SEM. But those are the things which are happening there, because if you want to do a backscatter kind of imaging where you want to look at the interactions that are happening from the backscattered electrons, you're always governed because of the electrons which are coming from the inner shells. When your beam is being interacted through the nucleus, it's coming through them. That happens when you're operating your SEM at much higher voltage into a range like here, the maximum range has to be set as 30 kilo electron volt. That probably might somehow interfere with the lower limits of TEM imaging, where you are pushing your electron gun that higher, where you are almost making your opaque sample to be transparent sample, and you're getting some information from the depth into the sample. But that's not that much accurate with respect to TEM. That's why they say that they only work with electronically transparent samples or specimens when you're working with TEM, or opaque samples when you're working with SEM. But it's not the thing that, okay, we don't have those things in our body. We have, that's why we are like mixture of everything, and nature has everything in us. Okay.
Okay, ma'am, I got it. I got it because in the presentation also, all that the sample shows, it is barium chloride, aluminum.
Yeah, it's all chemicals. Yes.
So that's the reason I'm coming to the conclusion. Okay, biological sample means SEM. There is a metal, barium, aluminum, chloride means SEM like that. One of the multiple choice question also it is came in the morning. So
Mm.
biological sample which is convenient, SEM, chem, like that. There we choose like chem biological sample is most preferred magnification. So we will study from. I can learn from you in the next class. So because these
Definitely.
overall understanding is more important inside of the specific.
Yes, actually very important. Yes.
We are studying optical and TEM only. I think even if we are going to the 12 weeks also, we are staying about only these three microscope. Am I right now? Or we are going for
Yes.
EDOC or X-ray or Angur, what is that? Angur,
Oh, good electrons.
yeah, that detection or there where it is useful. That is also there in the upcoming weeks, ma'am. Or only we are staying about only three instruments. Or if there
I
is additional instruments are coming in the upcoming weeks.
I guess not. So this is like my portal. We have SEM there. Then you again, so you have elemental analysis of SEM, how it's of a TEM. Yeah, I guess you have, but it's very brief. Only 3 lectures on it. Characteristic X-rays, their absorption. So in that is X-ray, I guess you'll have this Auger electrons. And then you have basic some metrics into it. Intensity, that's it. Intensity. I guess in this one, X-ray diffraction, probably you'll have some information into there. But let's say for this year, so this is like my internal lecture content. I don't know if the professor decides and change some slides from it. So we'll have to see if something's changing from it or not.
We are discussing about only three instruments. We are not going in this subject. Maybe X-rays. No. X-ray detector we are not discussing here, right? Because X-ray spectroscope.
Detector not, but within SIM, how you can get those characteristics that we have been discussing. Okay.
Being huge information, very rapid. I need to increase my catching strength.
Okay. I guess that this is like when I took this course as a TA, I also thought that okay, it would be good and okay, even I would be able to learn something after interaction with all of you. Each and every day, I feel that okay, this is a new thing that I've learned this time. Even not after looking at the lecture, but also after interacting with all is like, or even with from the discussion forum, it really feels that okay, there are still things that I don't know. Even though I've used this to electron microscopes, but I still feel that the SEM is a bit more easy to understand, whereas with respect to TEM, if you go and if you see, it really feels that okay, it's a bit more complex, very much complex. When essentially we go into the structural or lattice part of it, it feels very heavy to understand it. But yeah, it's like once you get through it, you get a practical exposure to it. You just feel that okay, this is the way things are, and that's how it works. Eventually, based on your specimen, you'll be able to take final decision that what you wanted to do on it.
Here I am feeling that very complex area is the mathematics, where
Yes,
we can
that's also
expect
true.
the mathematical question in the question paper. Which area we need to practice ourselves for that one. Based on the assignment area, we can expect that similar kind of the questions we can come or not. That is only the area I feel the complex, because whatever the assignment I have filled the mathematical question, it's become a wrong, because one
Ah,
area they are giving the options. Okay, another area even that answer is not giving any explanation as well after correct.
Okay.
So there is learning capacity. The scope is very much less in the kind of mathematics involved in the questions. So that area really, how many mathematical question is involved in this final examination, really I don't have a clarity on it. I
I guess
hope
that's the thing you can add in the discussion forum and directly tag the instructor there. Because if you add in these questions, probably he'll be able to help you with more mathematical questions, or probably he'll give some more mathematical questions to solve, and that will perhaps improve your understanding for it. Because yeah, that's true. If you solve more problems, you'll be able to get an idea or practice through it. If not, then it becomes quite difficult when you just do one example and then you feel that okay, similar example will come, but the logic is different for some other example, and you get that. Mhm.
we need to first I like to know which area we need to focus for the mathematics. Then we can make practice
Mm.
at different way. For example, I understand n lambda is equal to 2d sine theta. So this formula using one question will be mandatory as I understood until now. The rest of the idea, I don't have any clarity.
I guess I can ask. We have a meeting on next week, probably coming by, so I can ask him for numerical examples and the weightage, right, in the exam.
Sorry, ma'am. Sorry, I can get you.
You want to know about the numerical examples and their weightage in the exam, no? And some more examples to solve.
Oh, yeah. What is the percentage of mathematical question will
Weightage,
be
yeah, sure.
there? And
I'll
then
definitely
the
ask this.
topic area, we need to focus on that in the out of 12 weeks. Not we are not focusing on only 6 weeks. Out of 12 weeks, which
Yeah.
are the topics? Which are the topics of the mathematical question area? We need to more practice on it. There we will get the help from books or another ChatGPT or
Which
Gemini.
particular topic? Sure, definitely. I'll ask
Because
him.
that
I'll ask him that.
remaining
Yes.
understanding of spectroscopy or magnification or resolution or whatever the terminology they are saying depends on how it is changing or where it definition. This are all it's not a big what is a rocket science to gather,
Yeah,
but
that's true.
yeah, that we can understand easily with focusing on our concentration. But I'm
Yes.
feeling struggle only the mathematics area, ma'am. So that
Yeah,
the next
yes.
meeting, ma'am, we can have something input from you that will be more appreciated, ma'am.
Yeah, sure. I'll definitely ask this. You can
Okay.
also do one favor to me that you can add this in the discussion forum. I'll also ask in my in-person meeting. But if you ask this, that would be something that also the website TAs get to know about it and they can tag the instructor for it also. So that it's like,
Where,
okay, directly coming from the students, but not the TA also.
where
Okay.
it is, ma'am, where I can do that? It's a feedback
Uh,
form. It is coming all the time.
no,
Where it
if you
is?
go here, you go into Q&A.
1 minute, ma'am. You are sharing the screen. Okay.
Yeah. Yes, and this is my personal one. Yeah. So here, like, if you see, so
Okay.
this is already completed. Wait, I'll just show you for the new one. So if you go here for Q&A,
Okay.
you
So
will
yes.
be able to see. So people have asked questions for their request for marks, which particular question they want it to be reviewed. So
Yes.
TAs will reply for those questions. Like if you see over here, some another TA, Mehtab Alam, he's like a PhD student from a professor's. So he
Hmm.
has replied that, okay, these things would be done after the session, these things would be clarified. So you can just add in here and tag them that, okay, we have been facing these issues for numerical. So here you also see that most of the people who are facing issues in numerical questions, they have been asking questions. And for them also, like they have said that, okay, they'll solve and get to them after that. So probably you can also question back and I'll also tell them so that they also think that, okay, that's a thing. So here they said, right, that this
Oh,
mistake was on our side. We forgot to mention the unit and the answer should be written. We'll discuss this and update you accordingly. So
okay.
then it's being
Oh,
affected. That.
okay, ma'am. Okay, ma'am. I will do that. Thank you.
Yeah, yes, exactly. Okay, so where were we? Here. Yeah, so we saw how SEM works. Then we more or less discussed this part, the raster scanning and spot by spot, one by one for TEM versus SEM. We saw this digital signal. So yeah, there's one thing I also wanted to explain before closing this session. So yeah, this is elastic inelastic scattering, phonon scattering. So these all are fine. One thing I wanted to explain was,
Hmm.
mhm, So if you have this is your specimen, and this is your operating region in your specimen, whereas this is your image. Okay. Now, what we always do is for your beam, the spread of your beam defines your resolution cell. Okay. So, actually, how much can you differentiate in between 2 points? Laterally, how much can you differentiate in between 2 points? That is nothing but said as your axial and lateral resolution eventually gives you your information about your resolution cell. Okay, so what you do is you define a particular resolution. So your resolution cell is comes from the geometric properties of your electron beam, eventually is dependent on the gun and from the aperture of the gun. Okay, so that being said, you have a kernel, something like this. You take a kernel which has some x comma y dimension from your resolution cell. It can either be, the kernel can either be sized to your resolution cell or can either be some integer multiple of the kernel cell. Okay, now what you do, you take this kernel, so you take this kernel, move it across, move it across, again move it across, move it across, move it across, move it across. And this is your specimen, so where your finally image would be formed, or your region of interest where you actually want your image to be formed into. So one thing that I want you should know, that you all should know, is that when you form it for one particular image, how our pixel reconstruction is being done, that we take the centermost pixel, the intensity is being given to the pixel right here in our image. So that is how it's like raster scanning it through this, and through this our entire image of some cross x cos y dimension is being formed over here. Okay, so if you want to image a structure or a feature in your specimen, what do you think? What should be the size of your resolution cell? Should it be higher than that of the specimen that you want to image or the feature you want to image, or should it be lower? If it's higher, what will happen? If it's lower, what will happen? These are the things we want you to be cleared on, because if not, then you won't be able to understand the image reconstruction part of it.
It will be bigger, ma'am. Definitely, it's
Exactly.
bigger.
Exactly. So most of the times it should be bigger enough so that it covers the size of the feature that you want to image. If it's more bigger than that, okay. So let's say this is again your specimen tray. This is your some specimen feature that you want to image. Your kernel can be maximum related to the size of the feature that you want to image. So this is just kernel that you are trying to image. If it's more than that, you'll get the diffraction related effects into it, and your image would be blurred eventually. So it's something as doing a low pass filter on your image. So what you want to do in that particular scenario, if this is your specimen, you take a smaller kernel, smaller kernel, smaller kernel, smaller kernel, move it, move it, move it here, move it here. So in that way, you'll eventually get a map in your image that is stating that, okay, you have something, that feature is being told over there, and you get a physical dimension of that particular feature that you are trying to image. So people do this characteristics when they are trying to image something as nanoparticles, when they are trying to image something as hydrogels, because now they are not known that, okay, what the features are or what exact features that they try to image, that they want to image, or fibers or fibroids, something like that. So in that cases, they take a kernel size which is lesser than the feature size that you want to image. Whereas in cases, if you know that, okay, you have a clot that you have placed, or you have a composite kind of material, or something as alloy kind of material. In that case, you take your this kernel size greater than the feature size, so that it's only a single feature that you want to image, and you are no longer concerned with the entire structure of it. So if it's the entire structure, the pixel size should be lesser, or your kernel should be lesser than the feature to be imaged, so that you differentiate in between two features. If it's not, then it should be greater than that, so that you just get one feature that you are trying to image. Okay. So this point was clear, because that's really important during image reconstruction. Next is elastic scattering and those parts. So I guess we can look on this in the next session. It's more as chemistry in here, and we have already looked at the structures previously also. So more in depth, I guess it's not needed that much, but it's just basic chemistry. So this X-ray, this Auger electrons, or Agar electrons, how you spell it. So from where it's essentially coming and what all discussion we just had, just based on it. This thing is not yet relevant now. So we'll look at in the next session when the assignment would be relevant to it. These are like inelastic scattering. So yeah. Yes. So here you see this pair-like structure. So that only eventually comes from your inter-element interaction. When that comes, you detect that particular electron, you finally make image with respect to that electron. Okay. So we'll pause in for the lectures for this slide. We'll continue from this slide in the next session. So if there are any further questions, you can let me know, or we can do the assignment questions.
Sorry, ma'am, I can get you. Finally, what you said?
If there are any further questions till this part, we can discuss, or else we can go to the assignment, because the part that is next to it, it's mostly from the basic understanding that we have discussed previously also and that we discussed today also. Most of the slides I was giving content from this also. So we'll discuss this more in detail from the next session, because that would be more relevant to the assignment that we'll have that time. So that solving questions with the relevant context and text becomes more easy so that you get in the information into it. Okay, so if there are any questions, you guys can let me know. If not, then we can go to the assignment.
No more question, ma'am. No more question. We can go for assignment.
Anyone else?
Yeah, no more question, ma'am. We can go for assignment.
Here. So that's it. We have like our week 5. Here, week 6 assignment. Week 5 we already did. Okay. Oh, I guess it's blurred out. Okay. So elastic scattering. When does it happen? In the backward direction involves deflection, forward direction. Backward direction involves deflection, or mostly in the forward direction and involves deflection in smaller angles. Which one? So this is kind of a scattering where you don't have any energy loss. And it's something which is relevant to the reflection. So in which particular direction will it occur?
For me, I'm a little bit confused about B and D. I know it's a forward direction. There is no backward direction. But smaller angle, higher angle, both it is possible, no, ma'am. For example, backscattered electron, it is coming with high angle, I believe. For secondary electron, it is coming with the lower angle, I believe. So
Yes.
really, please help me, ma'am. I'm not sure about it.
So exactly the thing that you just said. Secondary electrons are coming from smaller angles, coming from the lastmost, then interacting into the innermost shells. Secondary backscattered electrons, they do interact, but they are coming from the higher angle. But backscattered electron, when come to the surface, they lose most of their energy. And eventually, the contrast that we see from backscattered electron, we need more voltage so that we can get some contrast from them. So essentially, they lose the energy there. So here we are talking about elastic scattering. That means that our collisions are with no energy loss. So hence, the answer to that comes in smaller angles. So essentially, we are talking about secondary electrons here.
Okay.
The amount of secondary electron generation is expressed in terms of what? So, okay. Yes.
V, ma'am, secondary coefficient
exactly.
or yield.
The coefficient or yield is directly given. Okay, characteristics X-rays, I guess. Okay, they are used in SEM for what? So through characteristics X-rays, you get information about which of the following is like topological. So just think of it. From where do you get the characteristic X-rays? From which particular part of your, if you just assume a K element shell, from where do you get it? So if you just know it, you know the answer for it.
Chemical analysis, ma'am.
Exactly. So sometimes characteristics X-rays, though the answer here is chemical, will also give you information about the atomic number contrast, because eventually you're going into the innermost shells. The heavier an atom is, more dense it is with protons, it does give, but people don't acknowledge it for that. They always say for the chemical analysis or elemental analysis. So that's just for chemical analysis then. Yeah, here. So how it tells you about the elemental analysis, but they never talk about the atomic number related contrast. So probably not. Okay. Our electrons are generated at where? So are they on the surface with higher energies, smaller energies? Do they contain information about the topology, or are they favored in terms of small binding energies and the bulk of the specimen? So we do know that, okay, it comes from the denser ones. From where then?
I think it's B, ma'am.
B.
Yeah.
So surface of the specimen first, and it is favored in terms of smaller binding energies. Why? Because it's just coming from here, such as a K shell, it's just being removed. So it's like directly coming from the innermost shell and telling you about the lesser must energy. So they are, it's like decay that happens due to the lower binding energies of these electrons. Okay. White radiation X-rays. So of course, these are ones with the higher bending energies. So how do they appear? Do they appear as a background in the spectrum, occupy certain specific, occur a specific wavelength, or as background EDS?
Really, I'm
I
very
guess.
new for white radiation of X-ray. I am not familiar with two different X-ray radiation. First of all, there is a two different radiation is there, ma'am, in X-rays, white rays and the black rays in X-rays.
So
Characteristic.
one you have is characteristic X-rays that
Uh,
are giving you information about the chemical analysis coming from the intel is like the innermost shell. The second you have is the white radiation, which occupies as the background in the spectrum. So those aren't actually giving information about the elemental analysis, so how they are saying in the background, but here the answer would be somehow relevant to the characteristics X-rays. Whereas the upper one, it is just telling you, so it's coming from everywhere. That's the thing, it is being told as a background. So if we just see it here, so it's due to the deceleration of the electrons. It's not specific to any particular element. It will just come. So the energy spectra for it, it's very broadband and very wider range of energy.
Understood. But when it will come, ma'am, X-ray characteristics, we know that whole flow chart, we saw that one. But this, it's totally new for me. When the white radius is coming, why, in which process, in which electronic state relaxation process, or how this, what's the energy of it? And really, I don't know how to understand this white radius.
We can look on it, but I guess how it's saying in the explanation is that it's not specific to any particular element, but it's just due to the deceleration of the incident X-rays. So we
Not
can
giving
see if we are related to the energy sources, how much energy sources it goes to. We can look on it. I'll write it. Energy.
8, model
Mm,
6. Okay.
yeah.
Okay, ma'am. I will refer this lecture 28. 1 minute. Ma'am. I will note it down.
Yeah, this one. Yes. Okay. So in SEM, calculate the backscattered current. I guess we didn't see that, but to achieve the backscatter yield of this 0.8 for a primary beam to have a current of 2 microamperes. So what to do for that? It's just a direct relationship in between current and yield. So you have your backscattered yield. I guess the
Yeah.
formula is given over here. So you have backscattered yield, you have your current in the backscattered electron by the primary beam electron. Okay. Primary beam current. So just in a way, you can get this information, you can get the current from there. Okay, so the answer for this is 1.6. Okay.
0.8
Similarly, you can also compute the yield for secondary electrons. If you know the current for the secondary electrons, you can compute for it. Or if you know the yield for it, you can compute that also.
So this is formula is 0.8 divided, oh, 0.8 multiplied by 2.
Yes, so you get the current for it.
Uh-huh.
Okay.
Okay.
So this we didn't see, but we do know about it because we have discussed. So there's phonon scattering. Don't look at the term, but in electron specimen interaction. So it will give you what information about the chemical contrast. So just remember which particular shell it was coming on. So you'll know the information to it. So is it any? So is it a chemical? Is it contrast or is it diffraction?
Phonon, it is happening. What stage? Phonon, plasma, I know. Phonon, it's happening at what? Elastic waves. I understand. It's very less. Phonon scattering is for. It's not chemical analysis. I know very well, ma'am. Maybe contrast. None of the above. Useful diffraction. Maybe C, ma'am.
The diffraction related information.
Yeah.
Yeah.
None of the.
Yeah.
So it will not give you any studies. Yeah, you're right.
No information from phonon scattering.
No any use. Even diffraction or contrast or chemical.
No, because well, it might help you with the defects or impurities in some cases, but that to be for crystals, but not in diffraction, not with contrast, not with chemical information. So it's like when a high energy electron beam interacts or strikes an atom, you get phonons, but they don't carry any useful chemical information for imaging purposes because the energy loss is that higher in there. So because yeah, it's a function of temperature and the atomic number. So temperature is like as in how the temperature increases, it will limit your thermal conductivity. As that increases, it is more relevant in conductors or semiconductors, can tell you about the impurities or defects in a crystal structure or scatter like that. But in your regular, nothing about the contrast, chemical analysis, or your diffraction related information, because those things don't even come there.
The function of what is that, ma'am? Lastly, it's function of temperature and what's that? It's
temperature and atomic number.
Generation of photon is although a strong function of temperature and atomic number. So this is the factors that the phonon is coming out. Okay, ma'am. Okay.
Yes, exactly. Because it's not coming essentially from the material, it's coming from in the material. There's something that's happening in the material, some vibrations that are happening inside it. Due to that vibrations, the scattering is getting reduced, energy loss is getting increased, and that's why you won't be able to get any of the terms related to it. So it's like mostly you don't get anything from it.
Okay, ma'am. Okay, understood. Clear.
Scanning mode in SEM will tell you what. Scanning mode in a SEM increases the pixel size, increases the resolution, doesn't affect the image. Does affect the resolution in but what way? And
the pixel size, ma'am, I think so. Or
yeah,
I think I believe. Oh, it's C. Okay.
So your pixel, we already talked. So that pixel is eventually dependent on what? Your image size, the smallest size that you want to image, or your electron beam size, where you actually want to image. It's a function of your electron gun, your gun aperture, and the way that the step size in which you're trying to image. So your pixel size is eventually dependent on that. So it's basically everything related to image reconstruction. But where it increases your resolution in a way, why? Because I told you that we are essentially overlapping the pixels moving along, overlapping, moving along. Here also overlapping, moving along. So that way we're able to get all the information that's lying in a particular feature. We are overlapping it, so we are getting most of the information. We are not losing it. So in a way, we are increasing the resolution, raster scanning it. Okay. So that's like the entire
through pixel, no, ma'am.
Sorry.
It's through pixel mode, right, ma'am? SEM is working on the pixel mode. Am I right, ma'am?
So it's not a pixel, it's just a kernel, or you might say it as a window. And in that particular window, you have multiple pixels. But when you say that it increases the pixel size, pixel is eventually the smallest in a unit in your image. So that goes on till your image reconstruction. It's something that is happening post imaging or post scanning. The question that we're trying to address here is through scanning, what happens? So because we are trying to scan, we are able to get most out from our specimen, most of the features out from our specimen. So in a way, we are increasing the resolution. Unless as TEM, where you're only specifically doing some spot by spot imaging, in that you're only getting information about a single spot, higher resolution. But if you see about the entire image, that will be nothing but a lower resolution. Okay.
But which microscope it is going by pixel, ma'am? It's a SEM or TEM or optical? Pixel by pixel resolution basis. It's which microscopy, ma'am, you have?
We never go pixel by pixel.
Okay.
We take a collection of pixels. So we take
Okay.
a window of pixels.
Okay. Okay, ma'am. Got it, ma'am.
Yeah. Okay. Elastic scattering occurs mostly in, so I guess we just saw it. Forward and inverse reflection in smaller angles.
Yeah.
Backscattered signal. So the backscattered signal from the specimen is capable of yielding information about what? The surface topology. Electron structure.
Oh, both surface topology and composition imaging?
Yeah, so why composition? Because you can do EDS analysis there.
Okay.
Exactly. In SEM, what do you do? Spot size, smaller spot size. Okay. Smaller spot sizes will require higher brightness and contrast levels. Smaller require lower. Spot size does not affect. Spot size does not affect. Okay. So the smaller will require which level of brightness then? And contrast. In case will require higher. So if your spot size is smaller, feature that you want to image is also vacant size there. So you need more energy within that particular spot size. So you need more of brightness, so more voltage, and hence you can detect the contrast levels in the detector that way. Because this does not hold to that it does not affect. Eventually, how much spread your beam has, is related to that how much area or how much spot are you trying to image it through. If it's lesser, so you need more energy there so that you can get information about all the structures and hence you can get a higher contrast eventually. Is that fine?
Yes, ma'am. Yes, ma'am. I'm trying to catch. Okay, this for me explain some smaller spots. Current. Beam current.
Okay.
Real down. You are uploading this, no, ma'am? There I can take this print and everything, no?
Yes,
right,
yes.
ma'am? You are uploading this question
yes,
and all, right?
Yes,
okay.
Yes.
Okay.
Yes. Okay.
SEM.
So in SEM, yeah, we just discussed this. Larger the raster, the greater the magnification or the size of display. The smaller the greater, smaller the larger the greater, or larger the smaller the greater.
So the larger the raster dimension or the size of the display, the greater the image. Smaller the raster dimension and the greater the magnification. I believe B, ma'am. Oh, it's a C. Smaller the rationalization and the larger
the size of the display.
And the greater is the magnification. But B and C is missing is the larger the size of the display. But remaining everything is okay.
Yes.
The size of the display, smaller the raster, and the size of the display.
Exactly. So that is how you need to know that where are you imaging? Where are you imaging? That being said, as in your specimen and your display, how much bigger it is or smaller it is. That's why we are scanning this way also, scanning this way also, actually also, laterally also, and eventually making it a bigger image. So our magnification is increased in that way, like that. Because this is also true. But for which size of the display?
Yeah, that time overlook, I think. Yeah, the size,
Exactly.
the display should be also larger, right, ma'am?
Exactly.
So,
So that you get your feature magnified.
yeah,
Okay, so choose the appropriate one for the secondary electrons.
C1 electrons are produced by primary electron beam in upon the specimen surface and the characters by the narrow depth. SU1 electron produced depth inside the specimen to the primary. No, SU1 electrons are produced due to the backscattered electron. No, SU1 electrons are produced from the depth in. No, that is A, ma'am.
Exactly. So when you just read secondary electrons and deep inside, just leave it. Or due to backscatter, leave it. From deep side, just leave it. Just look at the first one. From primary electrons that are impinging on the surface and are characterized by the narrow escape depth. So when being said this escape depth, it determines the sample size of our this pair that's being created after scattering. So that's our escape depth.
What is the meaning
Hi.
of escape depth, ma'am? I'm not understand, but actually I answered only that it's coming from the specimen surface area. That I'm very clear. But this I'm not understand. Narrow escape depth. What is that? What is the
Yeah,
meaning?
so it's being escaped at smaller angles and not traveling that much distance, right, into your specimen. So it's just coming from the outermost shells. So that is nothing but narrowly it can go out. So the depth it requires to be penetrate is lesser. So yeah, escape faster. Okay. Okay. SEM and TEM differ in which way?
Of imaging technique, contrast generation, and performance magnification. Yes, the way of magnifying technique and performance magnification. This is also right. The way of performing magnification and contrast generation only. The way of imaging technique only. Oh my God. The way of imaging technique and the contrast generation and performing magnification. Imaging techniques and performing contrast generation is the question. Contrast means bright field contrast or dark field contrast. I think A altogether. Yeah.
Exactly. Imaging
But I'm
technique is
not
also
clear.
different. Yeah.
Contrast generation. I know imaging technique by spare parts itself. I understand the imaging technique. There is so much of lenses are involved in TEM. So
Mm.
then magnification also it is very high TEM. TEM is compared to that it's low. It's better than 1 nanometer. That is 0.2 nanometer can work in TEM. But what is the contrast generation means it's a bright field, dark field kind of things, ma'am.
Exactly, those things only. Because here in SEM, you don't no longer have those objective lenses, whereas you have these in TEM, so you can control the contrast from there in here. Whereas here, you don't no longer play with the diffracted beams. It's just your direct beam that of electrons that is going and getting reflected back. Okay. So next, the contrast produced in same image is for what? Higher for heavier elements, lower for heavier elements. Okay, so we have different modes here. Is it higher for heavier elements in the secondary mode or lower for heavier elements in the backscattered mode, lower for heavier elements in secondary, or higher for heavier elements in the backscattered?
Contrast, that means dark. Dark when it will come, that's a question. Heavier or, yeah, heavier, it's right. Heavier it will be become dark, more contrast.
Yes.
But it is in
Yes.
secondary mode or backscatter mode. That's a question now.
Yes.
Heavier in topographic information, that is atomic information. So we need to discuss only secondary part. Heavier for D, ma'am.
Yeah. So why do you think it's D? Because you get contrast here and not here?
Sorry, ma'am. Sorry. What you said?
Yeah, so why do you think it is D? Because like we in backscatter electrons, we know that essentially when it comes up to the surface, the electrons have lost most of the energy, and it's essentially inelastic scattering that's been happening over there. Whereas in case of secondary electrons, what happens right there? So it's just almost a similar energy that we are getting back on the specimen, and that space energy is not eventually that high enough so that you can differentiate and make contrast within your image. Whereas in case of backscatter electron, you know that which particular energy you initially shined onto your sample, and then which energy is now eventually returning back to the specimen. So that energy, the lesser in energy, and the difference in between these energies are the ones that will make a contrast difference there.
But here, ma'am, the SAR is shown that images of secondary electron image is separate image and the backscattered electron image is separate image. So both the image is shown in one slide in the video. There, I understand that one, that both it is not involved in to make one images. So it is having two images used by secondary electron is one image, then backscattered electron. We can get that information. But here, same images means we can say it is two images. Same image, there is a two images possible, I believe. I don't know about that X-ray and Angor images, also separate images, or this is supporting to these two images as well. Really, I'm not clear. Since I'm not operating the instrument, I don't know how many images we can take for the one specimen. So here, even secondary mode also, I saw that images, there is a darker and whiter elements visible. In backscattered also, there is a darker and whiter is there. But backscattered, it's showing more contrast difference compared to secondary. The reason there is a very high electron volts are present in the backscattered mode.
Backscatter one.
So that means, so we need to choose D.
Yes.
Even lower electron, higher electron. So yeah, you are writing the same thing. So
exactly.
We need, but that only two types of images only possible in SEM-MAM, or even X-ray detector. It will show X-ray image, no, ma'am.
No, you won't have those images. So again, that depends on the detector that you have in the system. So if you have those kind of detectors, of course you can make. But the classical systems, they only come with secondary electron imaging. They come with backscatter electron imaging. Then based on that, these imaging, we also have some low magnification imaging and you have high magnification imaging. After that, you have your imaging characterized in terms of working distance. So how much beam and the specimen is being placed apart from each other. Based on the working distance, also you have image. Now, if you have multiple detectors, you can take an image from the characteristic X-rays, you can take an image from the Agar electrons, but if not, then the classical ones are only these two. Okay, so I hope that was clear and we are done with the assignments for, let's keep it for this week. If you have any further questions, can let me know. Thanks for attending.
Yeah, only one, ma'am. Last section also you shared this kind of question, ma'am, in the last previous section as well, or it is?
Yes.
You shared that assignment question also.
Yes. Everything shared.
The end of the what is that live section?
Yes.
Yes, I joined after that in the working time. That time it's a working day, so that I maybe jumped to off mode, I believe. That's the reason I missed. This is today I'm leave actually. That's the reason I'm totally capturing all your information. Thank you.
Okay.
I will see your videos, ma'am, whichever you uploaded. It's a really useful, ma'am. Really, it's very useful. Your questions, especially. So I will go through that. So, ma'am, for the examination point of view, which reading material, because we are unable to read the books and all. It's impossible.
Yeah.
Even we are a college student, we can do that one, but we are working and to do that very difficult. So only watching this videos and this kind of live classes can help to pass the examination, because I need to score that very reasonable marks as well, not just like passing. So
that's true.
Which way you are directing that study material means which one I need to take the printout now. But you take that to the presentation, that's enough, or this question, each live section question will help me to understand better, or the assignment, the real assignment which we given the answers are corrected, So we can expect any kind of same identical question or the similar question may be present in the examination. Which way you are directed? I think you already attend this kind of NPTEL courses. Really, you have past experience as well.
Yeah, so when I gave, it was mostly similar to the assignment questions. This week and that and the questions that we are solving now are the questions from last year. The questions that have been given to you are the freshly made questions. So if you are able to solve these two questions with like no particular problems or issues, and now if you have understood those problems very accurately, if you have gone through the lecture questions, so in lecture also professor sometimes will give you some examples, and from there he won't calculate, but he'll eventually show you there are some numbers in classes in the lectures. So just if you go through them, it's like more than enough information for you to like score more than 75. So that is from my own experience. But if you want to solve more, then yeah, you can go through the references and can solve from the textbooks. And
Thanks. Thanks a lot.
okay, thanks for attending.